Alright, so in this video I'm going to be explaining another important article about domain adaptation, but this time it's in the semi-supervised setting. And we are doing source label adaptation. So this idea in 2023, which is about source label adaptation. Semi-supervised domain adaptation involves learning to classify unseen target data with a few labeled data. So semi refers to those few labeled data, and lots of unlabeled target data, along with many labeled source data from a related domain. Current SSDA approaches usually aim at aligning the target data to the label source data with feature space mapping and pseudo-label assignments. Nevertheless, such a source-oriented model can sometimes align the target data to source data of the wrong classes, degrading the classification performance. So, class alignment is very important. We call it class alignment. It's an important constraint that should be included in your modeling of domain adaptation. Otherwise, it maps it to the wrong classes. So this paper presents a novel source adaptive paradigm that adapts the source data to match the target data. Our key idea is to view the source data as a noisily labeled version of the ideal target data. Then we propose an SSDA model that cleans up the label noise dynamically with the help of a robust cleaner component designed from the target perspective. Since the paradigm is very different from the core ideas behind existing SSDA approaches, our proposed model can be easily coupled with them to improve their performance. So on the top you see training the model with the original source labels might lead to a misalignment of target data. But on the bottom here, you see that after cleaning up the noisy source labels with our SLA framework, the target data can be aligned with the correct classes. Here you see all of the classes are mixed, so it's not good. But here you see circles are with each other, squares are with each other. So this is a feature visualization, and we always use this TSNE algorithm, which is a 2D visualization algorithm. For example, when you want to go from one source to a target, and they model it with ResNet 34. We observed that misalignment has already happened at a very early stage. Guided by source labels and few target labels, a portion of target data from the 59th class misaligns with the source data from 7th class. So you see that there is some misalignment. Here there is a misalignment. So the problem setup is that it focuses on a K-class classification task with M-dimensional input space, and we have labeled source data and we have labeled target data. I mean, because it is semi-supervised, at least you have some labeled, a few labeled data. And then this is the losses that you're working on. The LS, this one is the loss derived from source data, but these losses are the losses from labeled and unlabeled target data. So this is an overview of the proposed method. Like many articles, they use feature extractor and then classifier. But for source data, we adapt the original source label to better fit the target feature space by the protonet with pseudo centers and calculate the label adaptation loss. For label target data, we train it with a standard cross-entropy loss. We can apply a state-of-the-art algorithm to derive the unlabeled target loss for unlabeled data. For every specific interval, we update the pseudo-labels and pseudo-centers to get a more reliable label adaptation model. Noisy label learning. The effectiveness of the machine learning algorithm highly depends on the quality of the collected labels. With regard to the present deep neural network design, the aforementioned issue could worsen as deep models have capability to fit the dataset in seemingly random manner, regardless of quality of the labels. So to clean the noisy labels, this reference proposes a smoothing mechanism to mix noisy labels with self-prediction model. And the 26 models clean labels as trainable parameters and designs a joint optimization algorithm to alternatively update parameters. So these references estimate the transition matrix to correct the corrupted labels. However, learning a global transition matrix usually needs a strong assumption of how noisy labels come from, which is a bit difficult to verify. But this reference trains the label correction in a meta-learning manner. So we propose a simple framework that can effectively build label adaptation to correct noisy source labels. So we propose this algorithm which we seek an ideal model G star that can minimize the unlabeled target risk. So ideally, the most suitable label for a source instance X sub I in the target space should be this ideal model. That is, the ideal source loss is this entropy. Is just cross entropy between H is just the cross entropy between the two distributions. Because here you have access to the ideal model. And combining with the label target loss, we refer to the model trained by L sub S and L sub L as ideally adapted source plus target. The results reveal the full potential to adapt source labels. So in practice, however, we can only approximate the ideal model. We don't know it. So to address this issue, we take the original source label as a noisy version of the ideal labels and approach as an NLL problem. We first apply a simple method to help correct the source labels, which we refer to it as label correction with self-prediction. We refer to it as label correction with self-prediction. For each source label instance, X sub I, we construct the modified source label Y sub I. This is the modified, which combines the original, this is the original one, and the prediction one, and the current model G with ratio alpha. Then the model source loss is now this entropy. However, in domain adaptation, such a method might not be helpful since the model usually overfits the source data. And so you see in figure 4 the KL divergence from y sub s to g at each iteration. It shows that when doing label correction with self-prediction, the KL divergence from y sub s to g could be close to 0 after 2000 iterations, indicating that the self-prediction is almost the same as the original label. So in this case, doing the correction is nearly equivalent to not doing so. To benefit from the modified labels, we need to eliminate supervision from source data. As an ideal clean label is the output from the ideal model G sub S. We should instead find a label adaptation model. This is a label adaptation model that can approximate the ideal model. So here we use the idea of protonets that, protonet, I've explained it in my playlist for few-shot learning, and it's one of the most important methods for few-shot learning. So we just withdraw inspiration from that few-shot learning article, because here we can create some prototypes for each class, for example, class K. So CF collects all the centers with extractor F. It's a very intelligent way of, very simple kind of, if you have clustering in your mind, then you understand it, what you are doing. So we have some cluster in our mind. We define P as a protonet with centers. So the probability is just the distance between your protocenters and your extractor. And so you get the probability of each instance. And D is just, as I said, it's a distance measure over feature space, usually Euclidean space. This T here is a hyperparameter. It controls the smoothness. When T goes to 0, it means that the protonet is like a uniform distribution. But because we have access to labeled target dataset, again, I'm saying it's because it's semi-supervised. Semi refers to those few labeled data. Then we can derive the target centers. And then with the current model, the pseudo label for an unlabeled target instance is just optimization problem. After deriving unlabeled target data with pseudo labels, we can get pseudo centers and further define a protonet and protocenters. Then the modified label is again, instead of that kind of modeling that we promised, is now in the previous slide, this one. We replace it here, and then now we have the modified labels. And finally, we just propose a label adaptation loss for source data to replace the typical source loss with standard cross-entropy loss. For each source instance, we first compute the modified source label, and the label adaptation loss is here. So L sub L is the loss function for labeled target data, which can still be a standard cross-entropy loss. In contrast to other widely used methods, we primarily concentrate on improving the usage of source data. Therefore, the loss function for unlabeled target data can be derived through any state-of-the-art algorithm. And then we have warm-up stage. Our label adaptation model relies on the quality of the predicted pseudo-labels. However, the prediction from the initial model can be noisy. Thus, we introduce a hyperparameter, this W, for warm-up to get more stable pseudo-labels. During warm-up stage, we train our model normally with original source labels. So at the eth iteration, we compute the modified source label. And this is when you go from one source to a target, you get different accuracies. But it is a semi-supervised approach.